Now, what is the radiation heat exchange between two bodies or between two surfaces? So this can be easily understood with the help of by taking some examples like the sun rays coming from the sun to the surface of the earth. It is a basic example of radiation heat exchange from sun towards the earth. So basically the heat exchange is completely possible with the help of electromagnetic waves. So these waves carrying heat energy and further it travels from one body to another body and penetrate on the surface of the body and release all the heat and energy to that surface. So heat transfer in the form of electromagnetic radiation. So it is the only mode which does not require any medium, like in convection or in conduction. So there is a requirement of medium that can be a material medium or within the body. So without that medium, it is not possible to exchange heat exchange between two bodies. But in the case of radiation, it does not require any medium. So very popular example or practical example is sun rays from sun towards the earth. In between sun and earth there is a very large distance, so beyond the atmosphere from the earth, so there is no medium available there, but in fact the heat in the form of electromagnetic waves coming from the sun towards the earth. So like a means of basic life on earth. So we can conclude with the help of same example now which we had discussed. So here is a different band. If you can see bands, we can say that. So how the wave propagates under the wavelength. So radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. Some of the waves, some of the heat energy, this can be easily visible with the naked eyes, but on the other hand, ultraviolet rays or gamma rays or radio waves, which can't be even possible to see with the help of naked eyes. So there is a visible reason which is suitable for the human eye. Or the second thing is that everybody have its own temperature. Everybody emits radiation, like human body due to thermal ability to transfer heat from inside to outside. So there is a certain temperature of everybody which is present inside the atmosphere. So here is the scale of temperature in centigrade or in Kelvin. So by the color coding, it can be easily defined whether the emission of heat or absorptivity of heat can be easily taken place with the help of these color codings. So it is a conventional example of stove having utensils. We are just boiling the water in the pan, or it is a simple example of the three modes of heat transfer. One is conduction from the stove. There is a heat exchange from the surface of pan. Here the conduction takes place. After that there is a water. So water, generally the mode of conduction is convection because there are two separate mediums. After that the third one is from stove to the metal, the heat exchange with the help of radiation. When we apply heat to the body, then it emits energy. It emits energy in the form of radiations, in the form of electromagnetic waves. Like all objects generally emit, absorb, transmit or reflect radiations. When we heat the object, then it radiates the heat from its surface. As compared to the shiny surface, a dull or dark surface is the better emitter. So this is the radiation. Now the greenhouse effect is generally described with the help of radiation phenomena because sun emits the radiation under the intensity of 343 watts per meter square. So first of all, the heat energy in the form of electromagnetic waves come out from the sun and enters to the atmosphere of the earth. So near about half of the radiations absorbed by the earth's surface. So after some of the solar radiation reflected back by the atmosphere and the earth's surface. So some of the infrared radiation passes through the atmosphere and into the space. So some of the radiation are generally scattered from one body to another body and absorbed by second body or third body. So it's like a chain process. Then the radiation is converted into heat energy, which causes the emission of long wave infrared radiation back to the atmosphere. If there is a medium in between the electromagnetic wave and the earth's surface, then the medium generally absorbs some amount of heat. A part of the radiation gets absorbed by this particle. If the medium is not absorbing type of, then the radiation passes undiminished. The basic fundamental concept of radiation is emitted in different wavelengths and different directions. Like one is spectral distribution, second one is directional distribution. So in spectral distributions, it is depends on the spectra of light, or like we already discussed about the different wavelengths. So every microwaves have their own wavelengths. So it is a most important characteristic of the radiation. And second one is directional distribution. So it's generally depends on the direction of the light because waves have to follow the direction of light. Whenever a body plays a part in the radiation process, the radiation comes towards the body and some of the radiations got reflected back. Some part of the radiation absorbed by the body and some is transferred. So basically, reflectivity shows by the symbol rho, absorptivity by alpha, and transmittivity by tau. So the first is reflectivity, the ratio of reflected radiation to incident radiation. What is the incident radiation means the actual amount of radiation is coming out from the sun. So what is the intensity of that radiation is given by the intensity. So incident radiation, the radiation comes, incident radiation come towards the body, some is reflected back, some is absorbed and some is transmitted from that body to the other side. So now this is a absorptivity alpha, the fraction of incident energy that is absorbed alpha. So amount of heat absorbed but divided by the total heat coming towards that surface. So transmittivity, like same fraction of incident energy that is transmitted through the object. So tau is equal to G transmitted, means amount of radiation transmitted divided by the total amount of radiation coming towards the. So by applying the energy conservation law, all the three radiative properties depends on the wavelength and the temperature and the value 0 and 1. So we can also say that one is means 100%. If alpha plus rho plus tau is equal to 1, we can say that this is energy conservation. Now we can find the value for the exact absorptivity, reflectivity or transmittivity of that particular body. Now what is the black body radiation? So it is believed that the black body is an ideal emitter. No other surface can emit radiation more than the black body. So that's why energy emitted by an ideal or the real surface, energy emitted by any real surface is less than the ideal. So the ideal one is black body. So there are some assumptions involved by assuming the body is a ideal. So it is an ideal emitter at every frequency. Like it emits as much energy as or more energy than any other body at the same temperature. So temperature is a major contributor towards the radiation. So it is a diffuse emitter. The energy is radiated isotropically, independent of direction. The monochromatic emissive power, E lambda. It is defined as the rate per unit area at which the surface emits thermal radiation at a particular wavelength lambda. Like what are the monochromatic? These are such radiations which are characterized by a single frequency. So in a practice, like radiation of a very small range of frequencies which can be described by stating a single frequency. The wavelength in air or in vacuum is also used to characterize a monochromatic radiation. Black body has the highest E lambda for any given wavelength. Black body radiation, like different bodies may emit different amount of radiations per unit surface area. But in case of black body, it emits the maximum amount of radiation by a surface at a given temperature. So here is the difference between two bodies. One is black body and one is real body. So here is one in the black body, the emission is uniform, or in the other case there is a non-uniform emission. It is an idealized body to serve as a standard. We can take black body as a standard. Black body is a perfect emitter and absorber of radiation. So because it is an ideal case, so that's why it's a perfect emitter and a perfect absorber. Black body absorbs all incident radiations regardless of wavelength and direction. So this is a basic equation for the radiation heat exchange, and the radiation energy emitted by a body which is black is EB at given temperature is equal to sigma T to the power 4. So T raised to power 4 means, so directly proportional to T raised to power 4. As the temperature is more, then more heat can be emitted by a body. So emissive power of black body is known as Stefan Boltzmann constant. Sigma is a constant of proportionality between energy and temperature. So here is the value for the sigma is 5.670 to 10 raised to power minus 8 watt per meter square Kelvin power 4. So the equation gives the total emissive power of a black body, which is E is equal to sigma T raised to power 4, which is the sum of the radiation emitted over all wavelengths. For specific wavelengths, we can calculate the spectral black body emissive power. So here is a Planck's law. So the amount of radiation energy emitted by a black body at a thermodynamic temperature T per unit time, per unit surface area and per unit wavelength about the wavelength lambda. So E for black body at given wavelength and given temperature is equal to C1 upon gamma raised to power 5 E raised to power exponential C2 upon lambda T minus 1 watt per meter square micrometer. So C1 and C2 are the two constants. So C1 is 2 pi hc squared and C2 is hco by k. So there are some values for the constants which are C1 and C2 by with the help of experimental data. So here is the Planck's criterions for a perfect black body. So allow radiations to enter but not reflect. It possesses a minimum thickness adequate to absorb the incident radiation and prevents its re-emission. It also satisfies severe limitations upon scattering to prevent radiation from entering and bouncing back. Now the emissivity, it is the ratio of emissive power of a body denoted by E to the emissive power of a black body at the same temperature is called emissivity or hemispherical emissivity of the surface, and the symbol is epsilon. So epsilon is E upon EB. So E for the radiation emitted by the body over as compared to the black body. So emissivity depends upon temperature, wavelength and surface smoothness. So emissivity of the black body is one in the most solid and liquid. The radiation emitted from interior are absorbed by the adjacent molecules, thus making its a surface phenomenon. In gases and semi-transparent solids, radiation is a volumetric flow. So here are some definitions about the Wien's displacement law. The black body radiation curve for different temperatures peaks at a wavelength inversely proportional to the temperature. So lambda maximum into temperature is equal to constant. So where T is the absolute temperature in Kelvin and C is having a value of 2.898. It's also called Rayleigh Jeans approximately. So Wien displacement law can also be explained by integrating the black body with respect to different wavelengths. Like from the spectral distribution of black body emissive power, it is apparent that the wavelength associated with the maximum rate of emission depends upon the absolute temperature of the radiating surface. So from the Planck's law, it is given by E lambda is equal to C1 lambda to the power minus 5 upon exponential C2 upon lambda T minus 1. So if we differentiate here with respect of lambda and setting the derivative equal to 0, then it will be maximum. So we can find the value maximum. So by integrating, so there is a value for C2 upon lambda T is equal to 4.965. 4.965. So maximum lambda T is equal to C2 upon 4.965 and it is 0.0029, where lambda maximum denotes the wavelength at which emissive power is maximum. So the Wien displacement law may be stated as the product of absolute temperature and the wavelength at which the emissive power is maximum is constant. Also, this law suggests that lambda maximum is inversely proportional to the absolute temperature, and according to it, the maximum spectral intensity of radiation shifts towards the shorter wavelength with the rising temperature. So next is what is Kirchhoff's law. So to understand the Kirchhoff's law, we have to select two bodies. So in the figure 7.7, we can easily understand what is the Kirchhoff law. So first of all, there are two bodies. One is perfectly black body and other is non-black body, like real surface. And the temperature of the black body is at Tb. We can say that the temperature of the black body is Tb, and for the non-black body the temperature is T. So the two surfaces are arranged in such a manner that the whole amount of radiation falls on the other body. When the non-black body emits radiation of intensity E, then the whole of the radiations are completely absorbed by the black body. So the radiation emitted by the black body or black surface then is also strikes to the non-black body. If the non-black body surface has absorptivity alpha, it will absorb E equal to alpha EB radiations. The alpha EB radiations and the remainder 1 minus alpha into EB will be reflected back for full absorption at the black surface. So there is a radiant interchange for the non-black surface equal to E equal to alpha EB. If the both surfaces are at same temperature, then T equal to TB, then the condition corresponds to mobile thermal equilibrium, so which is given by E minus alpha EB, which is also E. So E minus alpha EB equal to 0. So from here E upon alpha is equal to EB. So this relationship is constant because when one body reflects radiation towards the other, then it reflects back, then again, so this process is going on. So with the help of Kirchhoff's law, it can be easily understood or explained with the help of the continuity of the radiation exchange between two bodies is E1 upon alpha 1 for the first, E2 upon alpha 2 for the second, and E3 for the so on. So it will be equal to the for the black body. So the whole of the heat emitted from the one body and it is absorbed by the other body, and then again it is emitted by one body and absorbed by the other body. Then this process is continuous and goes on increasing, and after that it will be equal to the black body. So this equation E1 upon alpha 1 is equal to constant like equal to EB. So it shows that the ratio of emissive power E to absorptivity alpha is same for all bodies and is equal to emissive power of black body at the same temperature. So this relationship is known as Kirchhoff's law. So from here it is clear that when one body emits radiation and it is absorbed by the other body, and alpha amount of heat is radiations gets absorbed here, and so remaining 1 minus alpha into black body again continues to the second case. After that this process is continuous. So ratio of this one is equal to EB. So EB means radiation emitted by black body, alpha is absorptivity, and E radiation absorbed by real body. So it is called E upon EB is called emissivity. E radiation emitted by a real body divided by, in that case if the emission is produced by the black body, then this is epsilon. So Kirchhoff laws can also be stated as the emissivity and absorptivity of the real surface are equal for radiation with identical temperature and wavelength. Here is also mean if we integrate from 0 to infinity E emissivity so with respect to small wavelength band, then it will give the value of epsilon equal to alpha.